Good afternoon to everyone present here. The student lecture will be given by Gauransh Kapur. He is a second year student doing BMath honors. His topics of interest are abstract algebra and number theory. I welcome him to speak on the topic of Carmichael numbers and primality testing. Please post any doubts you have in the meeting chat. They will be addressed at the end of the presentation. Over to you, Gauransh.
Yeah, thank you, Shankhu Bhaiya, for the introduction. So let me begin my talk first by welcoming all of you to the Limit Camp. I hope you all have enjoyed your lectures till now and hope that you all have a great time ahead. So let me begin. I hope my screen is visible. My screen is visible, right? Okay, cool. So let me begin first by mentioning Fermat's little theorem. Oh, I hope everyone here is familiar with some basic modular arithmetic. You can unmute yourself and tell me.
Yeah.
Are you all familiar with modular arithmetic?
Yes,
Okay.
sir.
Yes.
Okay, fine.
Yeah.
To some
Fine.
extent.
Okay, no problem. So I'll just recall, I guess, the notation. So we say A is congruent to B mod N if N divides A minus B. A and B here are integers and N is any natural number. Okay, so now let me state Fermat's little theorem. So this I'm sure most of you are familiar with or might have heard of the theorem somewhere. So Fermat's little theorem states that for a prime number p and an integer a, the following holds true. A power p is congruent to a mod p. Yeah, so this is Fermat's theorem. I'll just mention a few ways to prove this. I'll go into one proof, but I'll just mention some aside proofs. So there is one very nice proof which uses some combinatorial arguments and necklace counting. There is also another proof which uses properties of dynamical systems. There is a proof which uses induction. That is the simplest proof, inducting on A. And there is also a group theoretic proof which uses properties of Z mod PZ. So I'll just prove it one way, which is a pretty standard way, I think. So I'll prove a slight restatement, which is if A is an integer and A is co-prime to P, that is the GCD of A and P is 1, then A power P minus 1 is 1 mod P. So to prove this, we look at the set S, which is the set of integers A to A and P minus 1 times A. So our claim is that this set is a permutation of 1 to P minus 1 modulo P. So what this means is that basically all these elements in this set in some order, like when you divide all of them by P, all the remainders which you get are these P minus 1 numbers. So let's try to prove this. So there are two steps. The first step we show is that no two of these numbers have the same remainder mod P. So we show that no two numbers in S are congruent modulo p to each other modulo p. Okay, so for contradiction, let's assume that two elements of S are in fact congruent to each other mod p. So what this would mean is, let's say R times A is congruent to S times A mod p for some integers R and S in the range 1 to p minus 1 with R not equal to S. So now if we just write this into the divisibility terms, then this implies that P divides R minus S times A. So now we know that P is a prime. So if a prime divides the product of two numbers, it must divide at least one of them. So we must have P divides R minus S or P divides A. P divides A is not possible because we have chosen A such that A is coprime to P, and P divides R minus L. Well, let's look at this. So R and S are in between 1 and P minus 1 inclusive, which means R minus S is between 1 and P minus 2. Because R is not equal to S, the extreme cases are excluded. So this is also not possible because R minus S is less than P. So this would imply that P cannot divide R minus S. So we've shown that no two numbers of S are congruent to each other mod P. And the second statement is that no number in S is divisible by P. Again, this is also obvious. So say R times A is divisible by P for contradiction. This would imply P divides R or P divides A. P divides A is not possible by a similar argument. P divides R is also not possible because R is less than or equal to P minus 1. So this gives a contradiction, and therefore no number in S is divisible by P, and no two elements of S leave the same remainder when divided by P. So this means that S is a permutation of 1 to P minus 1 modulo P. I hope this is clear. If not, then you can ask me. Okay, good. So using this, we'll prove Fermat's little theorem. So let's begin the proof. So consider A in Z such that the GCD of A and P is 1. Then S, which is A to A, P minus 1 times A, is a permutation of 1 to P minus 1. Right? So now this means that if we multiply out all the elements of S, so if we multiply out all the elements of S, we get A power P minus 1 times P minus 1 factorial. This must be congruent to P minus 1 factorial mod P. Because S is a permutation of this set mod P, hence if you multiply all the elements of S, that product must be congruent to the multiplication of all these elements mod P. And P minus 1 factorial is not congruent to 0 mod P. In fact, it is congruent to minus 1 mod P by Wilson's theorem. So we can safely cancel P minus 1 factorial on both sides. and we get a power p minus 1 is congruent to 1 over p, which was what we had to prove. I hope this is clear. Okay. So this is what we are going to use to frame a primality test, which we are going to call Fermat's primality test. So the test is as follows. Pick a an integer such that GCD of A and P is 1, with P being a prime. Actually, no. See, sorry. Let A be an integer and N be a natural number such that GCD of A and N is 1. So we want to check if N is prime. So we check A power, we compute A power N minus 1. And if this holds true, then well, you might think that this would imply N being prime. But in fact, this is not always true. No, always. Sorry. Huh. So this in fact is not true. What I mean to say is that there are composite numbers. There are composite n which pass Fermat's test. So what I'm saying is that this congruence a power n minus 1 congruent to 1 mod n for all a satisfying this, there are in fact composite numbers for which this condition holds true. And these numbers are what we call Carmichael numbers. So these were discovered by, I think, Robert Carmichael or something in the 1900s or late 1800s. So these are very interesting numbers. Let me just state a few properties about them. So firstly, there is this criteria called Korslet's criteria, which is a necessary and sufficient condition for n being Carmichael. So it says that a natural number n is Carmichael if and only if firstly n is square free, which means that the factorization of n must look like this: p1, p2, pr, where all the pi's are distinct primes. So basically no square of a prime divides n. And it also states that p minus 1, pi minus 1 must divide ni minus 1. So basically, each of the prime factors minus 1, that should be a divisor of n minus 1, and n should be square free. If these two conditions are satisfied, then n is Carmichael. And if n is Carmichael, then it must satisfy these two criteria. So let me just give you an example of a Carmichael number. The smallest one is 561. And I think the next one is 1103. And then there is 1729. And so on. In fact, there are infinitely many Carmichael numbers. This is a very surprising result. And this was proven by, I think, Pomerantz, Wagstaff, and a few others. So what they showed that was the number of Carmichael numbers less than or equal to n. So this set had at least n power 2 by 7 elements for large n. And I mean, the proof of that result is quite complicated, so we'll not go into that. But yeah, using this bound, we can conclude that there are infinitely many Carmichael numbers. And there is also a very recent result by Daniel Larson. So Daniel Larson was a teenager, I think, when he proved this. Now he's probably 21 years old or 22. He's at MIT in US, I think. Yeah, so what he proved was that the Carmichael numbers satisfy a Bertrand-like postulate. So I'll just state Bertrand's postulate in a minute. So Bertrand's postulate states that for any n in n and n greater than or equal to 2, there is a prime p between n and 2n. So this is an interesting result which states that between any number and its double, there is a prime in between. So yeah, what Daniel Larson proved was that for large n, there is a Carmichael number between n and 2n. And he also got an improved bound, I think, on something like this, the number of Carmichael numbers in a range. So yeah, these are some things about Carmichael numbers. And I'll just state one last interesting result, which is a statement that n is Carmichael if and only if n divides the denominator of the n minus 1th Bernoulli number. So Bernoulli numbers are given by the following. So if you take the power series of x by e power x minus 1, you get a power series, and the coefficients which appear are the Bernoulli numbers. So there is this interesting result that n is Carmichael if and only if n divides the denominator of the n minus 1th Bernoulli number. And just as a side note, odd subscript Bernoulli numbers are 0, 4 and greater than equal to 3, 3 no 5, 3. So like B0 was 1, I think, except for B. Then B1 depends on convention, plus minus half. B2 is 1 by 6. B3 is 0. B4 is 1 by 30, I think. B5 is 0, and so on. So yeah, this Bernoulli numbers is a very interesting sequence. It has lots of applications in several areas. Like there are some interesting identities in combinatorics and graph theory and other areas which involve Bernoulli numbers in them. So yeah, this was a short thing about Carmichael numbers, and I'll just state something about Fermat's test. So the test was as follows. Let me just remind you. Pick an A such that the GCD of A and n is 1 for any number n, and we check if A power n minus 1 is 1 mod n. If this is true, then n might be prime. So if this is true, n might be prime. We don't know for sure because there are Carmichael numbers as well. But if this is not true, then n is certainly not prime. Not prime. And what I am telling you here is that this test has a 50% success rate, at least 50% success rate. So what this means is that if you pick a composite number n and you pick a random number a such that the GCD of a and n is 1, then the probability that n is composite is at least 50%. Like probability that a shows that n is composite is at least 50%. So what this means is that if you rerun the test with different values of a, with different values of a, the error reduces. Right, so if you run the test k times, the probability of the test being incorrect is less than or equal to 1 over 2 power k times. So yeah, it's a pretty good test, but due to Carmichael numbers, it's not the best test that there is. So there is an improvement of this test, which is called the Miller-Rabbin test. Miller-Rabbin test. So the Miller-Rabbin test is as follows. Let n be odd, because if n is even, then well, it's already composite. So then n minus 1 is an even number. So it can be written in the form of, in such a form where d is odd. Correct. Oh, by the way, I hope everybody has understood like whatever is going on until now and there are no doubts. If there's any, then just let me know. Acha, okay, okay. So now, since let me continue. So Miller-Rabbin test. So let n be odd, then n minus 1 is even. So it can be written in such a form. S is greater than 1, D is equal to 1. Okay. So now let's consider the Fermat congruence. A power n minus 1 is congruent to 1 mod n. I will rewrite this as a power 2 power s times d minus 1 is congruent to 0 mod n. Okay. And then here I use a bit of factoring, a square minus b square, the identity. So this you can factorize like this. Is this clear? This is like sort of domino effect. Like if you multiply these two, then you get a power 2d minus 1. Then there's a power 2d plus 1 here, so it becomes a power 4d minus 1, and the chain reaction keeps going on. Okay. So now we're checking if n is prime, right? So if n is prime, then it must divide one of the above factors, correct? Must divide at least one of the above factors. Numbers. और ये क्या हुआ, न्यू स्क्रीन आ गया, ओके नो प्रॉब्लम। चलो I'll continue with Miller-Rabbin. I'll share the notes of the talk later, like I'll prepare notes in later and I'll share them after the talk. Sorry for this. Odd. So, oh, so as I was saying, the Miller-Rabbin test. So we get this sort of multiplication congruence. So if n is prime, it must divide at least one of the factors on the left. Agreed? That's like by definition of a prime number. So if p divides product of some numbers, then it must divide at least one of those numbers. Okay. So this implies that if we want this condition to hold true, then we must have either a power d must be congruent to 1 mod n, or a times d congruent to minus 1 mod n for some r in this range. Correct? I hope this is clear. So at least one of these two conditions should hold true for n to be prime. If neither of these conditions hold true, then we can conclude with 100% certainty that n is composite. And this test, in fact, has a 75% rate of success. So it is much better than the Miller-Rabbin test. There are some counter examples, like it can so happen that you pick a base A such that the test shows you that n is prime, but in fact n is not prime. So yeah, but this test in general has a 75% rate of success. So it is much better than the Fermat primality test which we had. Yeah. So let me give you an example of a number. So let's say our number is 561. Remember, by Fermat's test, 561 was coming out to be composite. So Fermat's test was unable to detect that 561 is prime. But we look at Miller-Rabbin test now and see what happens. So let's take our base to be 2. Let A be 2. So n minus 1 now is 560, which is 2 cube, no, 2 power 2 power 4 times 35. So now n minus 1 is this, and we look at, so s here is 4 and d here is 35. So we check the conditions, we do a power d, which is 2 power 35. I'm leaving you guys with the calculation. I mean, I'll just show you what will happen. So 2 power 35 is 263 mod 561. And then we look at 2 power 70. So this is 166 mod 561. And we look at 2 power 140, which is 67 mod 561. And finally, if we look at 2 power 280, this is 67 square, I think, which is 1 mod 561. So remember what the test said. So either a power d was 1 mod n, or any one of these terms was minus 1. So what we can notice here is this is a power d, which is clearly not congruent to 1 mod n, and none of these numbers here. So a power 2 power times d is not congruent to minus 1 mod n for r in this range. So this means that neither of the above two conditions are true. Therefore, 561 is composite. So you can see that this test is much better than Miller-Rabbin's test because, sorry, than Fermat's test, because the outlier of Fermat's test, which was 561, has been detected to be composite by the Miller-Rabbin test. And you can say that 561 is indeed 3 times 11 times 17. So 561 is composite, and this concludes the Miller-Rabbin test. So, I mean, do you guys want me to prove that the Miller-Rabbin test has at least a 50% success rate? The proof for 75% is quite involved. It will take some time, but the 50% success rate, I think I can manage. However,
Yes.
it might need some group theory. So I don't know. I mean, I don't think any of you are familiar with group theory, right? But okay, I'll try. Let's see क्या होता है. Okay, so I'll state some basics from group theory. So, okay, a group G is a set with a binary operation dot such that, okay, so binary operation is nothing but a map from the G cross G to G. So A dot B will be something else. So when you do A dot B, they'll give you an element of G for A and B and G. Okay, so the first criteria that this map dot must satisfy is associativity. That is A dot B dot C is A dot B dot C for all A, B, C, and G. Second one is the existence of an identity. So there exists E and G such that A dot E is equal to E dot A, which is A for all A and G. And the last one is inverse. So for any A and G, there exists A inverse. This is the notation for A inverse. There exists A inverse in G such that A dot A inverse is A inverse dot A, which is the identity. Okay, so this is the definition of a group. Is this clear? I'll give some examples to sort of motivate what some very common groups are. So the first example of group is the integer z equipped with the operation of addition. So let's just verify. I mean, associativity is clear. Addition is associative over the integers. And it's also, there's also an identity, the additive identity, which is 0. And the inverse is also clear because minus a is the inverse of a, right? Because a plus minus a is 0. Is this clear? Okay, okay. So I'll ask you guys one question, and I mean, this is sort of obvious, but yeah, it's good if you can figure this out. Z cross dot, is this a group? The integers with multiplication, do they form a group? Anybody? Good. Yes. Think again. And somebody, if you want to unmute and give the reason, some reasoning. So remember, you have to check associativity, identity, and inverse.
There is no limits.
Yeah, exactly. Not all elements are invertible, right? So the only invertible elements are plus or minus 1. Element. So this is not a group. Okay. Now let me define a subgroup. So for a group G, any subset H which is a group itself under the operation in G is called a subgroup. Okay, and there is this criteria. So H is a subgroup of G if this is the notation for subgroup. If for all xy in H, xy inverse is also in H. This is called the subgroup criteria. So this is a criteria to check whether a given set is a subgroup of another set. So let me just give you some examples of subgroups. So the simplest example, I guess, AZ is a subgroup of Z, right? Yes, yes. AZ is a subgroup of Z because AZ is a group under the operation of addition, right? Addition is associative, and there is the identity which is 0, and there is also an inverse. So yeah, subgroups. This is the basic definition of subgroup, and there is a theorem. So this is basically like what are we using for the 50% success rate. This is Lagrange's theorem. I mean, I know now I'm not introducing everything properly with like motivation. I'm short on time, but if you guys go into higher math and read all of this, like group theory and all of these are very fascinating branches with applications in like almost every field. Yeah. So Lagrange's theorem is a very interesting theorem which states that let G be a group and H be a subgroup of G, then the number of elements of H divides the number of elements of G. So this is quite nice because it sort of gives you a criteria to check whether a set is a subgroup of a given group or not. This is for finite groups. but for infinitely, you can't talk about size that way. So yeah, this is Lagrange's theorem, which states that if G is a group and H is a subgroup, then the number of elements in H must divide the number of elements of G. Okay, so now I'll try to prove the 50% success rate, I guess. So consider the following congruences. X is congruent to minus x square is so on and so on. X times 2 power s minus 1 is congruent to minus 1 mod n. Okay, so uh, so these are like the congruences of the Miller-Rabbin test. Oh, so these are the congruences in the Miller-Rabbin test. And let x power 2 power j congruent to minus 1 mod n be the largest equation, the equation corresponding to largest j such that the equation has a solution. So basically, like, we are considering this system of equations and we are letting j to be the largest exponent of 2 such that this congruence has a solution. And let's call the solution x naught, I guess. Okay, don't need it now, but yeah. So let me just remind you, n minus 1 by r construct, like we defined n minus 1 to look like this, u power s times d, where d is odd. Now I define a set G. So G is the set of C in Z. Oh, I think I have to erase something. So I'll erase the group theory part. Like I'll send notes, I'll prepare LaTeX notes and upload them. So that will have proper some group theoretic introduction. Okay, so let's consider a set G, which is the set of C and Z mod and Z star. Now this looks weird, but this is nothing but the set of all x such that the GCD of x and n is 1. Basically, these are the invertible elements modulo n. Okay, so G is a set like this, such that C power D times 2 per J is congruent to plus or minus 1 mod n. So J was defined as follows above, and we are defining a set as follows. And I claim three things. The first thing is that if C is not a witness to the compositeness of n, then C is in G. So basically what I'm trying to say is if C satisfies C power n minus 1 is congruent to 1 mod n, then C must be in this group. That's what I'm saying. So yeah, this is easy to check. I mean, you guys can check this out. Because if C is not a witness to the compositeness, then well, what were the criteria? So our criteria was that either C power D was 1 mod n or C power 2 power t is equal to minus 1 mod n. Correct? So we said that if C was going to show us that n was composite by the Miller-Rabbin test, then sorry, if n was then one of these criteria must be true. So if C power D is 1 mod n, then obviously C power D times 2 power j is also 1 mod n. Just raise both sides to the power of 2 power j. So this implies that C is in G from here. Or even if this was true, then for then of course C power 2 power j times D will also be minus 1 power something 2 power j minus r. So yeah, minus 1 power any multiple 2 is like this is plus or minus 1 mod n. So even then C is in G. So I hope the first part is clear. So what we are saying is that if C is indicating to you that n is prime, even though n is composite, then C must be in the group G. Is this clear? You guys can show a thumbs up if it's clear, or I mean, if there's any doubts. Acha, okay, cool. So this and the second claim is that, well, this is a group. The set G, in fact, is a group. And I mean, fine, I'll verify that, I guess. So the first one is identity. One is there in G. No, not associativity. So like if A, B are in G, then I mean, so G is a group under, sorry. G is a group under multiplication. So I mean, associativity is easy to check. So the multiplication we're doing is just in integers. So associativity follows. And the identity is 1. And inverse, this is perhaps something. So let's say C is in G, then C power D times 2 power j is plus or minus 1 mod n. Now, I hope you are familiar with Bezout's lemma, which states that for x, y integers, there exist a b such that ax plus by is the GCD of. Yes, are you familiar with this?
Yes, sir.
Okay. So using this, well, we can see that if C power D times 2 power j is congruent to plus minus 1 mod n, then this would mean that n divides c times 2 power j plus or minus 1. I don't think we need this. Okay, got it. So let's say x was the, ah, let's say x was the GCD of c and n, then x would divide c power d times 2 power j plus or minus 1. X divides this already because x is the GCD of c and n. So that would mean x divides plus or minus 1. So the GCD of c and n is 1, and therefore c is co-prime to n. So if c satisfies the above congruence, then c should be co-prime to n. Okay, and now using Bezout's lemma, since c is co-prime to n, there exist x, y in integers such that px plus ny is 1. Okay, so this is the same as cx being congruent to 1 mod n, right? So in the set, like when you look at, sorry, when you look at G, which is the set of all invertible elements, so for C in this group, there exists C inverse, which is X, right? And X also, like the GCD of X and N is also 1 by this. So X is the inverse which we wanted, so there is the inverse as well. For any number C, there is C inverse X, and C inverse is in G. Why? Because Cx is 1 more n, so C power d times 2 power j. Oh, I think I have to love some more things. Sorry. So I think you all get it. Like Cx is 1 mod n, so if you raise both sides to the power of d times 2 power j, then you can check that x is also in the set G, and therefore the set G is closed under the multiplication is associative, and every element has a multiplicative inverse, and there is an identity. So therefore the set G is a group. So as G is a group, and well, the only thing which we need to show is that G is a proper subgroup. That's one thing which we show. So proper meaning that it is not the entire group. Like the set G is not the entire group of Z mod and Z star. So yeah, we've shown that G is a group. And the third thing is that G is not the entire group. So is there time? I mean, Shank over here is time till 3, right?
Yeah, there is time till 3, but you can extend for 5-10 minutes. No, that's fine.
अच्छा, ठीक है. Fine. So I guess I'll try and show this as well. So let's try to show this. So let's take P to be a prime which divides n, because we're assuming n is composite. So let P be a prime dividing n. Then n can be written like this. Okay, so you just take the highest power of P which divides n, and then the remaining quotient is not divisible by P. So now we had that congruence above x naught or d times 2 power j. So let x naught per 2 power j. So let x naught be a solution to that above congruence. So let's say x naught power 2 power j is minus 1 mod n. This would imply that, no, no. So let me now use the Chinese remainder theorem to do something. So by the Chinese remainder theorem, there exists a W such that W is congruent to x naught mod p power h, and W is congruent to 1 mod g, right? Because p power h and g are co-prime, so the simultaneous system of congruences can be solved by the Chinese remainder theorem. I hope you all are familiar with this. If not, then you can just check this up after the talk. Okay. So yeah, there exists a W such that this happens. And you can also check one more thing, that the GCD of W and N is wrong. So W is in our set Z mod and Z star. So since W is congruent to x naught mod p power h, and x naught power 2 power j was minus 1 mod n, so W power d power 2 power j is congruent to x naught power d times 2 power j, and x naught power 2 power j was like plus or minus 1. No, no, minus 1. So it was minus 1 by our definition. So this is minus 1 power d, and since d is odd, this is minus 1 mod n mod p power h. Okay. And also, W was 1 mod g. So W power d times 2 power j is congruent to 1 mod g. So this means that W power d times 2 power j is not congruent to minus 1 mod n. Oh, 1 second. Yes. Because g divides n, and since this is 1 mod g, it cannot be minus 1 mod n. And now I don't know, I'm getting a bit stuck here. So basically, I don't know, I'm forgetting what had to be done here. So at the end, I believe what we eventually land up with is that, well, this W is the one which satisfies, like, neither of the conditions hold true. So I don't know, I'm sorry. So like, yeah, I believe at the end, after some calculations, you get that this does not hold true, nor does this hold true. So this means that the number W here is in fact not in our set, because W is showing you that n is composite, and we showed that where any number which shows us that n is composite is not in our set. So W is not in our set G, so therefore G is not the G is not the entirety of Z mod and Z star. So this means that G is a subgroup, right? G is a proper subgroup of Z mod and Z star, and by by Lagrange's theorem. So this must mean that the cardinality of G is at most half, right? Because the number of elements in G divide the number of elements of this, and any number's maximum divisor is like it has to be less than or equal to half of that number. So, and G was the set of non-witnesses, right? non-witnesses, like the numbers which were telling you that n is prime even though it's not. So this means that there are at least, like, there are at most 50% non-witnesses. So there are at least 50% of witnesses. So the test has a 50% success rate. At least 50%. In fact, this is 75%, and that is a bit involved calculation, and we don't have time here. So yeah, I mean, I wanted to mention the AKS test as well. So I guess I'll just mention that and then we'll stop. Sorry for this can issue Canva का. I did not realize कि ये सब होगा. So I'll make proper notes of this and you will upload it on the drive and YouTube. Okay, I guess this would be sorry. And finally, we come to a test which has 100% rate of success. So this is the Agarwal-Kayal Saxena test, 100% success rate. And this is the first test which like runs in polynomial time and does not rely on any unproven conjectures to get some bounds. So the Miller-Rabbin test which I mentioned is it relied on a version of the Riemann hypothesis to bound the smallest number which satisfies the composite, which can show you that n is composite. So the runtime got affected by that. So here, this is one test which is 100% success rate. It does not assume any other conjecture. And so this one was, I believe, in 2002, August of 2002, by three Indian computer scientists, Agarwal, Kayal, and Saxena. So that's why the name is AKS. So Agarwal is Manindra Agarwal. He is now the director of IIT Kanpur. This Kayal is Nitin Kayal. I think Neeraj Kayal. I think he works at Microsoft, like researches at Microsoft in Bangalore. And this is Nitin Saxena. He was a graduate student under Professor Agarwal, and now he himself is a professor at IIT Kanpur. So these three scientists were the ones who gave us the AKS test. So the idea behind the test is as follows. This identity x plus a whole power n is 2x power in this. So this is the polynomial ring with coefficients from z mod n z. So this is nothing like, it's a set of polynomials with where the coefficients come from this z mod n z. And z mod n z is just the set of remainders when you divide by n. Yeah. So the idea is that this congruence, so this equation holds true in a in this above ring if and only if n is prime. This follows from the Fermat's theorem and then the binomial theorem. You can check. So this is the idea, and I'll just show you what the test says, like the procedure. So test. Step one is if n is a perfect power, output composite. or even minimum of power. So the first step, it just checks if n is a perfect power or even, and if it is, then it outputs composite. Now in the second step, it finds the minimum r such that all n is greater than n whole square. So this order of R mod n is the number k, is the smallest number k such that R power k is 1 mod n. So we find the smallest r such that the order of r with respect to n is greater than this log n base 2 whole square. And now we check one thing, which is the GCD of r and n. So if the GCD of r and n is 1, then output composite. So if R and N are not co-prime, then N is composite. Third step is for all two, for all A in this range, to and the minimum of R and N, check whether, check this, A does not divide N. So yeah, if A divides N, then N is composite. And the fifth step, so if the above four steps are done and n is not composite and in the fourth stage, then for um, for a from 1 to, so this is a weird expression, phi of r. So this is the floor function, which is the greatest integer function. So for a in the range 1 to the floor of, this is the phi function. So it counts basically the number of r, number of t less than equal to r, such that the GCD of r and t is 1. T is 1. And then it checks the congruence above, like this congruence, x plus a whole power n congruent to x power n plus a, but it checks it in a different manner. So not modulo n, but it checks it modulo something else. So x plus a whole power n, if this is equal to x plus a mod x power r minus 1 comma n. So this is like the ideal generated by x power r minus 1 and n. So this is something in ring. So this is just to reduce the time complexity. So instead of checking it mod n, they are checking it modulo this other expression. And if this is true, like if these two are not congruent for every a, then you output composite. And if this is true for all a in that range, so like if all the conditions till this step 5 are satisfied, then you give the final thing key that n is prime. So if all of these 5 steps are true, then n is prime. So this is the other work I also in a test, which tells you with 100% accuracy. So this has no counter example, and it's been like in the paper which these three scientists wrote, they proved that there is no counter example. So this test is 100% correct. So yeah, this was all I had to mention today, and I hope you all liked it.
Thank you, Gauransh, for your nice talk. Does anybody have any questions about the topics presented? If so, then please unmute to share your doubt. Okay, it looks like nobody has any doubts. So in
One
that case, yes, sorry.
share. Can I share a Jupyter notebook? I'll just show them. I wrote some codes for all these tests. So I'll just show that
We
for
will
you.
be uploading all of the materials you would like to share onto a drive. So just put them there. We'll share them at the end of the lectures.
Fine.
Like all of the works. Right.
Yeah.
So that's it for now. So thank you to everyone for attending this talk. Everyone is requested to join the next talk, A Tale of Two Cities with Coins and Tiles by Rishik Kole, which will be held at 4:30 today.